All right, the light is on. So I don't forget we're going to have a lecture tomorrow, and there will be no lecture next Tuesday. Okay, so next Tuesday I will not be here, but we'll have a lecture on tomorrow. All right. So we haven't done anything yet about Bayesian regression, so hopefully that's what we will cover today. But because I went extremely rapidly through this frequentist setting of what is called the Bias-Variance Decomposition, I want to come back to it and discuss it at least for the next 10 minutes or so. So let's summarize what we have seen, right? So we already saw that when you have a complex model with limited data set, when you do least squares, which is equivalent to MLE, you overfit, okay? And we introduced the concept of regularization that controls complexity of the model through the regularization parameter lambda. And we mentioned that in a Bayesian setting, that is not really an issue because you can have a huge number of parameters with limited data, but because you integrate them, that problem doesn't really come to the extent that comes in a classical setting. So what I want to do is I want to go back to this decision theory we did on minimizing losses and defining regression functions, and see how this formalism can lead to this bias-variance decomposition. The concept is not Bayesian, but you will see it basically written down everywhere, so it's something that you really need to know. So reminders, we're talking about regression. T is the target, y of x is our regression function, okay? So basically we want for each x to compute some function y of x to minimize the loss from the target t. We use quadratic loss, and we have shown that for quadratic loss, when you take the expectation with respect to the joint distribution of x and t, it is nothing else, y of x is nothing else, but at each x, the expected value of t, okay? And this is universal, all right? Universal result. So what you can do is, if you take this equation here about the expected loss, that's a definition, and you add and subtract this expectation, and you expand the square in 3 terms, all right? Like a 1 term squared, another term squared, and then a product of the 2 terms times 2. It comes out that the third term cancels out, and you get something that looks like this, okay? There's really no algebra, and maybe we discuss this in an early lecture, okay? So the expected quadratic loss looks like y minus the expected value of t for a given x, average with the distribution p of x, and then you have something here that does not involve y of x. So really, if you want to find the optimal y, all right, the optimal y is basically that value there, but I want to keep this expression for now written like that. So if you go and assume some model for y of x, this is how much loss you're going to have. This is the expected loss. All right, so we're going to say something about comparing models that somehow are going to give us different regression functions y of x. The last term, there's no dependence on y, so that term remains there as is. Okay, just to make the equations to fit on the page, what I'm going to do is I am going to assume that this conditional expectation, which is really the optimal y that you would like to have, I'm going to denote it as h of x. So just to remember for the next few slides, this expectation, I denote it simply as h of x, okay? I was thinking just before I came to go and change every slide and put this expectation directly, but hopefully you'll not get confused, right? So h of x is this expectation. So we would like to see where do uncertainties come in the predictions of this regression function. So if you do a Bayesian setting, and we have sort of motivated, right? So y of x is defined in terms of some parameters w. So let's say y of x is w transpose x, and those parameters w are random variables. So the uncertainty really in y comes from w, all right? But in a frequentist setting, there is no such a thing as W, right? So there's no uncertainty coming from there. The uncertainties that you will see in the predictions of Y in the literature come over different data sets that you use to train the model. All right? So imagine if I give you one data set, you go and you do some calculations and you find me some Y of X that gives some expected loss that looks like that. If then I give you another data set, you repeat the calculation, you find another Y of X. They're not going to be the same. There is a variability over the data set that you provide to the model. So when you see uncertainties in the regression function in a frequency setting, are uncertainties over data sets, not over the parameters. All right? They are not induced by the parameters because there are no parameters. So what I would like today is to discuss about this bias-variance decomposition, where we will see how these uncertainties in Y induced by different data sets, all right, are coming to give us this very nice decomposition that shows the this interplay, if you like, of bias and variance. Okay, so let me do some algebra. What I'm going to do is I'm going to define this expectation that you see here. Okay, D is my data set. Okay, so can you tell me what this expectation is? What does, with words, what does that mean? What is this expectation? It says there, but so this is the expectation of the regression function over data sets of the same size. So we don't, create more confusion. So all the data sets have the same size. So this is the expectations of this regression function over data sets. You notice the notation here, it says, for X, give me what the response Y is for a given data set. So now we're going to take many data sets, repeat the calculations of Y. So this is the expected value of these calculations. So what I'm going to do is, I'm going to take, you remember in the expected loss, the first term is Y minus the optimal, if you like, regression function, which was the expectation of T given X. So what I'm going to do is, I'm going to start with that and subtract and add this expectation of Y over data sets. Nothing major, okay? We add and subtract this expectation, and then you get the square of the first term that you see here, you get the square of the second term that you see here, and you get 2 times this times that. This times that, okay? So now what I'm going to do is, I am going to take an expectation of this with respect to data sets, okay? Here it was just an algebraic manipulation. I added and subtracted, right? Now what I'm going to do is, I'm going to take the expectation of this with respect to data sets. So what you're going to get is, you're going to get the expectation over data sets of this term, which is what you see here, the expectation of a data set of this first term, which is you see here, and this blue term is going to disappear. Why is that? That's why I put it in blue. So the blue term is going to disappear when I take expectation over data sets. Why is that? There is nothing to bother on this second term. Here you have the expectation of this minus the expectation of that, 0. Okay? So what you get is basically that the expectation of data sets of Y minus H squared is a bias term that tells you basically how this average over data sets deviates from the true value, the optimal value, that we call it H of X. And then a variance term where, again, the mean here is the expectation over data sets. Okay? Can you see it? So basically we have done 2 little steps, right? One, we added and subtracted to get something like this. And then we took expectations with respect to the data sets and we got this nice quantity. Remember the loss function, all right, involves on the first term an integral with the distribution P of X. So we are not really done. And the second term, there is nothing we can do. There's no Y there, so we are going to leave it as is. So what I'm going to do is, the equation we derive it I'm going to plug it in the first term so I can get the expectation of the expected loss function. And so we're going to plug it in there. And this is the final result that we're interested. So the expected loss, all right, it is a bias square term, okay, that you see here, a variance term that you see there, and the noise level, basically, that is going to stay there regardless what you do or how many data sets you have. So this key ingredient here of this bias-variance decomposition is that whatever models you use, either they're going to have very high variance and low bias, or they're going to have high bias and low variance. So we would like basically to discuss those type of activities in the context of regression models. And in the context basically of, you know, if you like, rich regression, where we have regularization in addition to the square error that we discussed on the last lecture. All right, so let me just discuss this with pictures, okay? And we'll do 2 pictures so we can move on. So what I want you to think is, think of least squares plus a regularization term, which is, I remind you, 1/2 times lambda times the W transpose W, okay? So what we will do is, we will, don't look first in the pixels, right? Think what happens when you use very high regularization. So the regularization term was 1/2 lambda W transpose W, in addition to the mean square error. So when the lambda is very high, what happens? To minimize that whole function with the regularization term, what needs to happen to the W's?
Zero.
A lot of them will get 0, okay? So if a lot of them will get 0, what type of models are you going to get? You're going to get like a straight line or quadratic, a very simple function, okay? So if you get a very simple function, you're going to have very high bias. And you can see here, this is the exact solution. It's a sign. And here, when you average over different data sets, you get something that is way away from the actual solution, okay? So you get very high bias, but because a lot of the W's are 0, you're actually getting low variance. You remember, that's why we use regularization to actually minimize the variability of the coefficients W. So for very high regularization, okay, you get basically simple models with high variance and low variance. And if we go, let's say, in another extreme, and we have very low regularization, that's when we discuss, right, that the coefficients start varying from very high to very low values. So you get very large variance, okay? But when you average all of these things together, all right, each of them is for a different data set. So when you average them, you actually get almost a perfect fit to the sine function. You get very low bias. Okay? So, I mean, this is, again, the non-Bayesian approach to this type of things. And you notice here, so here, sort of, you can say you average over data sets, right? In a Bayesian setting, we never average over data sets to do estimation. You know, we average, when you say Bayesian average, right, or model average, it refers to what? Let's say in the context of regression. What do we average when we do predictions? Over the parameters, right, using the posterior. But what you see here, you average basically over data. So in a Bayesian setting, and we'll discuss this in detail today, there's only one data set. That's what you're going to use. You don't have the luxury of lots of data sets. So the idea here is, you know what, if I have all of these data sets, I'm going to use all of them together to do predictions. Not say, do this for this and repeat, you know. And this is an unnecessary cost, so we will try to do a little bit better. But certainly there is a value to this bias-variance decomposition, so you need to be familiar with it. By the way, if you needs to write a computer program to compute this type of quantities, the obvious way to do it is to compute samples, right? And then apply Monte Carlo approximation to all of these integrals. So for example, if you want to compute this expectation, you will do a Monte Carlo average over different data sets. And then if you want to do this big integral that involves P of x, you will in addition take samples from x, and you will do another Monte Carlo approximation for that expectation, okay? So in the notes, you will see all these nice formulas, these blue lines, that basically approximate the variance and the bias square, basically. So if you want to plot these things, the calculation is not complicated at all. So before we move to the Bayesian setting, right? So and we leave out this bias variance decomposition. The common things both for a frequentist and a Bayesian person is what is the best model complexity to use. And we don't want to have the model complexity dictated by data. The model complexity has to do with the model, not what data is provided to you. So in a sort of non-frequency manner, you can see this model selection playing with this bias variance decomposition. So let me see here if I identify the colors. So if you increase the regularization that controls complexity, all right, this blue curve, all right, that you see here is the bias square. So you remember for very complex models, all right, you get very little variance but very high bias, okay? And for the reverse basically when the regularization is small. And then the opposite happens when you look at the variance, okay? So if the regularization is very high, there is no oscillations in W. Basically, you get very little variance. If there is no regularization, you get very high variance. Now, if you add the two things together, bias squared plus variance, you get this nice curve. And one of the tricks to select what is the optimal regularization is to take the minimum, the lambda that corresponds to the minimum of that curve. And that approximately is marked by that cross. Okay? And surprisingly, or not, when you plot the test error versus the regularization parameter, so you fix the regularization, then you start doing predictions on a test data set, it comes out that approximately the point where the bias squared plus variance is minimum, it's almost the same point where suddenly the test error starts increasing. Okay? So effectively, this, you will do something like that, right, if you play with model complexity, even in a Bayesian setting, and you can see there is sort of some commonality there, some relation from where that comes versus where these bias and variance terms together are minimized. So you can, again, use this to decide what is the optimal regularization if you do things in a non-Bayesian setting. All right, so let's become Bayesian from now on, okay? And so we said already that we're going to take the regression coefficients to be random variables, so we're going to assign a prior, and the prior that you see here, it's a Gaussian, okay? The precision of the Gaussian is alpha. M is the dimensionality of the parameters, so I have M parameters, and the way this equation is written, this includes the bias term as well. All right, I'm going to come back to that topic later, hopefully today. So all my coefficients W, this is the prior, and I want you to remember alpha is the precision of that prior, one of the variance. Remember alpha, okay, because it's going to come up in every slide. So alpha is the precision of the prior. All right, so we're going to, as a first step, before we can start doing any predictions, we're going to need to calculate the posterior of W. And everywhere you see bold letters, this basically means vectors. So this x bold is my training axis. This is my training responses. So this is a posterior distribution given the parameters alpha and beta. And beta here is going to be what? Can you extrapolate what is beta going to be? This is the likelihood, so what is beta going to be? I'm going to make the likelihood also to be Gaussian, right? We have I already showed you the equations for this on the last lecture. So what is beta going to be? Say it again. The what? It's going to be the precision, the noise basically in the likelihood. Okay? You remember the likelihood is basically the response t is the regression function, right? That's the mean response, plus some Gaussian noise, and that Gaussian noise has a precision beta. Okay, we will see the equation maybe in the next slide. I don't want you to read the rest, but once we're completely done, we're going to need sort of to do some corrections on the whatever we have discussed. And the only thing I'm going to tell you is the way I have it here, right? I mentioned this includes even the bias term, and is going to lead to regularization even for the bias term. You remember when you do regression, you say the regression function is W0 plus, let's say, W1 times a function phi1 of x plus W2 phi2 of x, etc. So this includes the W0 term, and you don't supposed to regularize the W0 term, okay? So that term should not be regularized because it is not the cause of overfitting, okay? So in a lot of books, for simplicity, they have it like that, but in practice, we will need to do something to correct it, and we will discuss later on. Okay, so imagine you have a prior that is like that, and you have a likelihood that's also Gaussian, that it was given again in previous slides, okay? And when you put the two things together, and you compute the map estimate, so in your head, all right, think this Gaussian, all right, think of the exponents of the Gaussians, right? So this exponent is minus alpha over 2 W transpose W. What is the exponent of this Gaussian going to be? Minus beta over 2. And what is the quadratic term going to look like? Would be that vector of the basis functions phi of x transpose times W minus t, right? The target values. So effectively, will you agree with me that if you do the map estimate, will be equivalent, so maximizing the likelihood will be equivalent to minimizing the exponent of the two terms added together. So from the likelihood you will get this, and from the prior you're going to get that. All right? Again, alpha is the precision in the prior, beta is the precision in the likelihood. So this is the square error that we have seen before, multiplied with this precision beta, and this comes now from the prior. And immediately you can see that's regularized the squares. So the map estimate you get right away before you even become Bayesian, all right, is the same as doing regularization. For now, the regularization is not sort of something with some mathematical abstraction. It's really nothing else but the ratio of the precision of the prior divided by the precision in the data, the precision in the likelihood. Okay? So effectively, if you do a map estimate, right, you will actually start with alpha and beta, and then that automatically will tell you what lambda is. And of course, you're going to tell me, yeah, but how am I going to select alpha and beta? And my answer would be, since you already have worked on this in the homework, we are going to have to do empirical Bayes, right? And we will discuss about that next week. Okay, but right now, alpha and beta is given. All right, so let me do some algebra, and these calculations, we have done them in extent in an earlier course. There is really, everything is in the slides, so I'm not going to go line by line, so I'm going to trust that you will read the slides and that you will use your imagination. So this is the prior, my nice Gaussian. This is the likelihood. You remember that's what we used before, phi transpose W minus the target values over summation over the data sets. So you can expand actually this square here to write like that, okay? And I'm only keeping terms that relate to W because I want to compute the posterior in W. And so you multiply this times that, all right? they merge in the exponential, and then the whole idea is to complete the square. Everybody knows what's a complete the square? You remember Gaussian times Gaussian is going to give you a Gaussian, and Gaussians look like this, right? So really you need to put this term here in something that looks like that. And whatever you get here is going to be the mean, and whatever you get there is going to be basically the inverse variance, okay? Covariance. And this is what you get, all right? So you get basically a Gaussian that has this mean and this covariance matrix, and the covariance matrix, it comes to be Sn inverse. It comes to be like that. And the subscript capital N that we use here is to emphasize that we have data sets of size n. So I give you n data points because I would like to investigate the effects of n later on in the lecture. So again, the posterior of W, right? So this is given the training data x and t, given the hyperparameters, we assume we know them. It's a nice Gaussian with this mean and this covariance. And again, I remind you, so phi of x is the basis functions that you use, okay? And just in case of you do polynomial regression, and again, you include the bias terms, you can have things like 1x, x squared, x minus 1, but you can put anything else you would like. All right, so that's a summary. Remember the symbol Mn. I'm using the notation from Chris Bishop's book. So Mn would be the mean of the posterior. Sn would be the covariance, and the formulas are written like that. And now, instead of using explicitly the basis functions, I use this data design matrix phi that we introduced in the last lecture, okay? So this is the mean, and the mean is the same as the map estimate here because it's a Gaussian, and the covariance is Sn minus 1 here. This is the formula. That's what we get. The covariance is Sn. All right. You can generalize this. There is really nothing. So basically, when we did this analysis here, right, we assume a very trivial prior, a Gaussian that looks like this. So you notice this is scalar here. So we assume that the precision is the same for all W's. So, but if you really want to generalize this and use a covariance for the prior that's completely arbitrary, the formulas are, you can work them directly. I think the proof is on the next slide. The posterior, you can update the previous formulas. They look like this, okay? So we, if this is again a general Gaussian, you can write down the posteriors looking like that. And so here is the proof. There is, you need to become experts on closing the squares for Gaussians because you can imagine if you don't do these things right and you start doing computer implementation for complex distributions without knowing that it's actually a Gaussian, that would be embarrassing, all right? So if it's a Gaussian, get it out of the way as a Gaussian, and usually visually, if you see W transpose W plus some linear terms in W, it's a Gaussian, okay? And that's what we use here. All right, so I mentioned that the map estimate is the same as the mean. There are lots of very nice formulas that you can derive, and I am looking here at this recursive formula. So you can imagine if you want to compute the posterior of W, but you want to update the posterior as you get data points. So suppose the data points come one at a time, right? So this tells you, you know what? No problem. If you want to calculate the precision where you collected n plus 1 data points, use the previous precision plus beta times phi transpose for the new data point. Very nice result. So this is like rank 1 updates for the precision metrics, and then with this precision, you can update the mean n plus 1 in a very nice manner, okay? I mean, this is sort of fundamental to the fact that everything in Bayesian analysis is sequential, all right? And these formulas They are basically not the exception, they are the rule for this type of calculations. So let's discuss a specific example to see what these things mean. So what we're going to do is we're going to start with a true function that is a linear function, some bias term plus a linear term with some given coefficients. So we're going to select some data points from -1 to 1. We're going to put some noise on them. We're going to do the linear regression analysis. We're going to fix alpha and beta to these values that you see here. Again, if you wonder from where they come, well, they come from somewhere that we don't discuss today, okay? And we're going to perform Bayesian inference sequentially. So we're going to compute the posterior of W, and for each sample from the posterior of W, we're going to be plotting the regression function, one data point at a time. I really like sort of these plots are universal. You should, regardless of what homework you get, you should actually try to look how these things work. So what you see here is 0 data points, and these are the contours of the prior. I mean, don't ask me now why they don't, because the prior here is supposed to be circles, okay? It's just a way that somehow this was plotted here. You can see -1 to 1 and -1 to 1. It beats me, but that's how they look like. You get what you get in life, okay? So all of this, you know what they are? How do I get all of this on the right? So you take a sample of W, and W includes W0 and W1, and for each sample you plot a regression function which is W0 plus W1x, and that's what you see here. So these are, again, samples generated from the posterior, in this case the prior, we have no data, and then we plot the regression function, it's all over the map. Now we collect one data point, okay? So this is the likelihood after you see one data point. This is how the posterior becomes. So it starts narrowing, if you like. And again, we take samples of W from here, and then we plot these straight lines, W0 plus W1x. And you notice most of these lines pass through the data point, okay? So this is not surprising, right? That's our evidence. So they try to maximize the evidence. So all of these lines pass near that point. If you collect another data point, this is how the likelihood will look like. So effectively here, actually, every time we collect a data point, the posterior from the previous iteration becomes now the prior, right? So you collect one data point, but the prior is the previous posterior, and this is the updated posterior that looks like that. These are the two data points, and you can see most of the lines start passing from the data points, and the posterior starts becoming narrower. You continue. Way narrower, there are lots of points here. It's like way down, several points have been collected, okay? And this is another implementation of the same problem. You can see eventually you are so confident about the posterior of W after all the data you collected, basically this becomes like a point estimate. And you expect this, right? Because at the end of the day, if you have lots of data, effectively maximum likelihood will give you the same answer, okay? But we did this process here sequentially, okay? And these are the way our regression lines look like during this iterative process. I think this is an implementation, the same exactly problem, the same data set from Murphy's book, so you can see another implementation. So, all right, we got W, we got the posterior of W, and as we have said a few times, we don't really care about W. W facilitates basically this concept of doing predictions. The objective is, how do we do predictions now, all right? And what you see there is the predictive distribution. I hope you can see the different symbols there. Again, this bold X and bold T are training data. The unbold X is now the new X that I want to do prediction, and that's the prediction T. And obviously that's a distribution. How do you compute it? you compute it likelihood times the posterior integrate of the parameters. So you say, if I knew W, this would be my the distribution of my prediction. I don't know W, so you average over the W coming from the posterior. And you can guess now, this thing here is, the prediction is a Gaussian distribution given W, right? That's the likelihood. We already computed this to be a Gaussian, and then you marginalize W out. Obviously, you're going to get a Gaussian, all right? So if you're lazy, you can go and say, fit me this to some Gaussian and start seeing what parameters you need to put in. But it's, again, way better if you expand those two terms, integrate W out, and then you will see a Gaussian coming for T explicitly. So what I'm going to do is, don't say anything about the algebra. I'm going to show you some generic formulas that you can use for these calculations, but basically what you need to do is plug in the likelihood that you see here in there. This is the posterior, which is this formula that we got before. You plug it in, and then you marginalize in W. So here are the general formulas that I have discussed this in other courses that you need to have in front of you all the time, because in this type of calculations with Gaussians, these are the type of operations you need to do. So these formulas tell you, if you have a condition distribution of y given x, and the mean is a linear function of x, all right, so you notice the mean is ax plus b, and you know the distribution of x, all right, so you can think of this like likelihood times prior, then actually you can integrate x completely out and write explicitly down the distribution of y, but also using Bayes' rule, you can invert this and write the distribution of x given y, and it looks like that. So one thing you can do actually is, one thing is you can trust these formulas and use them. Another thing you can do is you can prove these formulas once, and then you can come back to this equation and say, look, so for example, can you tell me what is A? So let me show you this, and tell me what is A on our real problem. Look at this equation again, P of y given x, P of x, and I want to marginalize, I want to do this. So tell me what is A. So you remember y is given x, and we said the mean is a linear function of x. What is x here? What is y? What's y? I mean, I'm looking here, right? What's y? T. And what is that metric say? What is, again, look at A. What is A? So the distribution of, you told me y is t, right? So that conditional of t, x will be w, given w, should be some linear function of w. What is that linear part? Phi transpose. All right? So basically, you can go and plug in all the right symbols, and it's done in the notes, okay, line by line. So you can cut and paste, and then by the miracle of nature, you get the final result that looks like that. The predicted distribution, once you train the system for a given x, on bold x, it's a Gaussian that has this mean that's a function of x, and it has this variance that's also a function of x, and here are the final results. Okay? It's wonderful that somehow we can actually now start doing predictions, and for each prediction, not only we know the mean value, which is what you see there, but we say something about the variance at each location x. And again, these formulas are not accidents. You notice here, this is the variance from the data noise, right? And this is the variance, obviously, from that comes from the posterior of W, because the two effects are additive. It's a linear model, okay? And so there is an amazing structure on these formulas that you will need to look carefully, because you may want to, generalize these models, or even better, you may want to use these ideas to put some intuition on the way later on in the course we will define Gaussian processes, okay? All right, so I am going to give you some sequential runs basically to see on how this predicted distribution looks like. But just to summarize, so once you train the model and you want a different axis to know what is going on, effectively what you will get is you will get a mean function, right? The mean of the predicted distribution. And these things are the error bars basically at each location x. So this type of plots, they are capable to give you point-wise uncertainties, right? So they don't tell you how the response at one location correlates with the response at another location. So for that, we will need to do some other type of plots. Now, the proofs are in the notes, but when you do these derivations, right, your head should spin and say, wait a second. What are the common sense results that I would like to expect if all of these are true? For example, is this something that you will expect as you increase the number of data points? I mean, if it doesn't happen, obviously you have a problem, right? You provide more information, but somehow your uncertainties point-wise, they are not less than before, there is an issue there. So you can actually prove this thing nicely, and it's in the slides. It's not a trivial, actually, proof, okay? But it's sort of a wonderful use of linear algebra operations that may be useful to your research to do this type of proof. So that's one. And another one, what do you expect when the number of data points is going to infinity? We have lots of data points. What's the best you should expect to be able to do when you have infinite data? To do exactly to reach the noise level of your data. Nothing better, all right? So you can actually show that this second term, was n goes to infinity, becomes beta minus 1. And actually, you can look at it from here, right? This is a Sn minus 1, all right? Okay, so when you take Sn is the inverse of that, all right? That's where you can immediately see here, if you expand this, the inverse of that, you can see that this thing goes to 0. So this is the proof I mentioned. It's in the slides. You just basically have to use this wonderful rank 1 updates of the inverse of the matrix. So if you add V transpose, or V is a vector to a matrix M, you can compute the inverse with this nice identity, and then you can show nicely that the variance as you add points is going down. All right, so let's see some schematics of the predicted distribution. So this is the mean function that you get when you have one data point. Okay, this is the generating function. So this is the solution from where we got the data with some noise, and these are the error bars. And you notice immediately from the first case, as you go further away from your data point, the error bars increase and basically go to infinity. Any method that you have, so when you do surrogate modeling, right, in any dimension, if you see your model away from the data giving you the same error as close to the data, then you know that your model is wrong. Okay, so don't even because people will ask you, how's your extrapolation? Can you extrapolate? Well, we have to be real. Yes, you can. I can extrapolate anywhere, but my confidence of the extrapolations is not very good. Okay? So if you use 2 data points, again, you notice around these 2 data points, the error looks, is minimal, sort of. Away again from this, the error is magnified. And again, this is now the mean regression function. By coincidence, it passes through the points in this case. If you use n equal to 10, all right, and you spread your points everywhere, basically your error bars look more or less the same everywhere, okay, because you have information everywhere. Of course, even for this trivial problem, if you're going to use 10 data points, somebody may say where this 10 data points should be, so that somehow my ability to do predictions for any arbitrary x is the best. And that's a very difficult problem. okay? And maybe one or two of you can pick up those things for the project. But again, the answer to those design of experiments equations for 1D or 2D or 3D functions is out there in the literature, but trying to push these calculations to 50 or 100 dimensions is not a trivial task. Okay? By the way, everything we do, you can use exactly the same program to higher dimensions. It doesn't mean it will work, but you can try. Okay? As a matter of fact, most methods are really extensions of what you see, and trying to fix the pathologies, the issues that exist when we try to extend this to high dimensions. All right? And so this is, I think it's the same sort of example, maybe a different data sets from Murphy's book, but he actually does a little bit something beyond on what the previous MATLAB program had in the results. He tries to do comparison with a plug-in approximation for W. You remember the posterior approximation, right? The posterior is the likelihood times the posterior integrating out all the parameters. So what have I done here to the posterior? We assume that the posterior picks around one point, and obviously that point would be the map estimate of the posterior. So effectively the result is like using the likelihood at the point X, but instead of any W, that W is the map estimate. You see that? That's the plug-in approximation. But can you tell me what is the noise level of the likelihood in our model? Like when we wrote the likelihood P of t given X, comma W, what is the noise level? You know, it's a Gaussian. And what's the noise level in that Gaussian? Beta. Okay? And you see here, it doesn't matter where you have data or where you don't have data, the noise is everywhere the same. That's why the plug-in approximations are very bad choices. Okay? So we mentioned the error should go up, you know, away from the data. That's not the case with plug-in approximations. Okay? So they're not good for you. But lots of people in machine learning use this plug-in approximations, right, in many problems. And sometimes they work because you have a lot of data. And really, the posterior is picked up, you know, it's picked around the map estimate. But in this case, you only have 5 data points, not enough, all right? So in that case, you can see the calculation basically, it's overconfident, so that's not good. All right? So let's do a different type of a plot now, okay? So suppose, you know, before we compute it at each point X, the point-wise uncertainty, right? Which, you know, that they come from the predictive distribution. We knew what the error bars are at each X. Now suppose you want somehow to to correlate the response at one location X1 with the response location at X2. How do you do that? Well, you do it as follows. Since you have the posterior, you draw samples from the posterior, and then you start plotting the regression function y of x in w. I mean, y of x given w. Okay? So I'm repeating. We want to be able how things are varying in 2 locations, how they relate to each other. Okay? So what you need to do is take samples from the posterior of w and then plot the regression function. And that's what we see here, the variability across different points for 1 data point, for 2 data points, all right, and for 12 data points. So if you really want to capture uncertainties in 2 different locations, this is the only way you can do it. You cannot do it by plotting the point-wise uncertainty the way we saw before. So I remind you, this is for capturing correlations at different x's, and this is, it tells you at each point how much uncertainty you have. Okay? They're all informative. This is good. You want to know how much confidence should be on the prediction there, but if you try to relate what's going on here with how it correlates with what's going on there, the only way to do it is by plotting this. So I think in your homework problem, we threw a little item somewhere, I think, on the last problem and said, plot this type of things. As a matter of fact, you know what? This type of approach, where you draw samples from W and then you plot a regression function for all x's, it's very fundamental because it really leads even to things like Gaussian processes. So I don't know if we're going to have time today, right? But I'm going to show you very briefly that somehow you can postulate, you can write down this regression Bayesian model using kernels, all right? And it comes out that the covariance at two different locations, x1 and x2, it's actually proportional to the kernel. And that's exactly what you do in Gaussian processes. You start with a kernel that kxx prime that correlates basically the response at 2 points, okay? Here we are getting this by taking samples of W and then plotting that. I'm giving you this thing a little bit ahead, and maybe we will see it today if we have time, or we will discuss it tomorrow. Okay. There it is. Okay, all right. Did not know in this sequence on the slides that this is this kernel representation. All right, so let's do the following thing. Let's summarize what the regression function looks like, okay? So remind me, what's Mn? According to the notation we have, what's Mn? It's the mean or the map estimate of the posterior of W, all right? So, so the predictive mean, all right? Actually, if you look back, right, in the formulas we have for the predictive mean, if you see it somewhere, tell me to stop, okay? So you can see here, the predictive mean basically is given by this, okay? And if you plug in, basically you look, if you go back on the derivation, basically the predictive mean is it's this, the same thing, right? Okay, so you can just plug in the map estimate on the regression function. You get the predictive mean. That's a good way to remember it. Okay. If you expand this, okay, you get like that. And you can remember phi consists of this basis functions phi of xn. So you can actually write that phi transpose t is a summation over each data point, and you get something that looks like this. It's all, there is no much algebra here. It's rewriting basically that phi metrics in terms of the basis functions phi, that each of the basis functions defined at the data point. And you notice suddenly we're getting something, some weights, if you like, that weight the responses at all the training points. So effectively it says, you know what, the response at any location x is some weighted averaging of the response at the training points, but with the weights depending on the distance, if you like, of x and xn. Can you see that? So you have a bunch of training points, right? And that, when you write this formula, it tells you if you want to find the response at x, it's really a weighted average of the training data, of the training responses, with the weights depending on x and xn, and most probably through a distance type of thing, okay? So, without knowing anything about what kernels mean, right, and I suppose you do because I will use them to some extent in this course, I am going to define this whole term there, beta phi transpose Sn phi, with x and xn like that. I'm going to define the kernel x comma xn. All right? It's something that effectively it's an entity that tells me how the response, all right, because this is what we look, the response between of the system at x and xn are related to each other. All right? How much variability do I get when I go from x to xn? That, in short, that covariance is captured by this kernel, but right now you can treat this as a definition. So why is this interesting? Because this formula here comes with some intuition, right? So what did we say? That when you look at So look at this formula. It says this, that the response at every x is an average of the response at Tn. Can you tell me which training points you think will be relevant to this point here? Will a training point down there be of interest? So somehow you expect these things to be very significant for points n, but they are very close to the point where you want to compute the response. And the rest are sort of insignificant. And look what happens. When you plot actually with some choices of the basis functions, and here I took the basis functions to be Gaussian kernels for some alpha and beta, and I took some training data. So when you actually plot this kernel function, it looks as follows. Concentrate on any given x, right? Let's say we fix x. This kernel becomes significant for xn very close to x in the diagonal. Everything else is nearly 0. And if you want to see this as 1D functions, if you fix the location x and you plot the kernel for different x primes, you notice it only picks for x prime near x, okay? So x here is 0.3, so x prime 0.3, that's where it picks, and here again, that's where it picks. So effectively, when you look at this expression, right, the maximum contribution is from xn that is very close to x, and the further they are, the less contributions you get. And this method actually leads immediately to another huge class of surrogate models in computational statistics that they're called smoothers. So you don't really have to do any Bayesian analysis. What you can do is, you know what? I am going to take the training data, put some filters, if you like, some smoothing functions that say, you know what? If I'm close to a training point, that point contributes a lot, away contributes nothing. Be sure the weights sum to 1, and you can do anything you want to. Right? You can derive 10 different methods. But don't get excited because people already did this and wrote lots of papers, okay? But you don't really have to be Bayesian to see that this is sort of very general, okay? And so it comes with its own sort of family of algorithms. All right. So we can write the mean of the predicted distribution as these kernels at x, xn, Tn. So that's what weights the responses of the training data. So this is an average of the training data. And there is something very interesting. You can use basis functions that have no local support. All right? I mean, Gaussians, you can have very local support, so you say, yeah, I can see why these kernels have this nice behavior where you get these contributions, high contributions when x is near x prime and everything else is around 0. But guess what? If the basis functions that you use to define these kernels don't have local support, still the kernels have the same behavior. All right, so what you see here, all right, doesn't have to do with the fact that the basis functions we use are of local support, okay? So you get the same behavior for the kernel for all the basis functions as well. So let me go back to what I tried to highlight, that effectively, you remember, so let me go back to this picture, all right? So I told you, when you draw samples of W from the posterior and you plot this, essentially, you capture the covariance between two different locations. So let's see what that means in terms of the kernel. Let's take two locations, x and x prime, and let's compute the covariance of the y's at the two locations. All right? So we take two locations, x and x prime. Let's compute the covariance. So y, the predicted mean is phi transpose w, all right? So at x prime will be w transpose phi x prime, okay? So I move phi transpose and phi x prime outside, and then I have the covariance of w transpose, okay? And I remind you, we're talking about the posterior now, right? So what's the covariance of w? It's a sen. Okay, so when I plug it in here, if you go back to the definition of my kernel, the kernel is beta times phi transpose is n phi. So when you look at this equation, basically this covariance of y's at two different locations, it's really proportional to the underlying kernel. And this is sort of another now Pandora's box opens, and you say, you know what? Now the kernel really captures the covariance at two different locations. And you may say, why do I need to bother to start with basis functions and do this Bayesian analysis? How about if I introduce directly a kernel and write everything in terms of kernels? Then you can do that, and the options you have are infinite. And these kernels don't even have to be related to basis functions. Right? They have to satisfy certain properties, and maybe we will review this when we talk about kernel methods, but somehow, all right, you can see that the plots I gave you that define this covariance between y at x and y at x prime, really they capture the covariance that is defined by the underlying kernel in this regression model. All right. Again, we're not going to be talking, we're going to spend at least one or two lectures about kernel methods because we need some advanced features in the remaining of the course. But I want you to think of the kernels sort of being inner products between high-dimensional future vectors. So in our, you can think of a kernel being some future of x psi transpose psi. That's an inner product. So it comes out, if you look at our definition of the kernel here, you can actually nicely write this as an inner product as follows. You can write this as psi transpose psi, where really this future vector is square root of beta, square root of this covariance matrix as n times p of x. Okay? So just remember that kernels, basically, this is the format that we will use, okay? Inner product of two future vectors. And in our case, basically, this is derived from the basis functions, right? The basis functions. And again, you can start thinking that maybe we don't need the basis functions, right? But right now, that's how we define the kernels. All right. Okay, so let me finish with this discussion on of not regularizing this this bias term. I ask you to do this in the homework, by the way, so at least I get one correct homework that actually does this properly, so we can go back maybe at another offering of the course and completely make the notes more complicated and start not putting a prior on the bias term, but let's see how you guys are going to do this in your homework set. So what I have done here, you remember, so let's talk about MLE to start with, right? The easy way. So if you talk about MLE, I took the bias term outside, okay? So the idea is, let's do something different for W0, okay? Because we said that it's not contributed to overfitting. So what I have here, I have m minus 1 basis functions, and I remove the bias term outside, okay? So if you want to compute the bias parameter, basically you can take derivatives with respect to W. The MLE estimate, right, is the gradient of that with respect to W equal to 0. So let's only compute the MLE of W0. So if you take derivatives and you expand, you get this wonderful result. Okay? T bar is what? Is the average of all your responses. And what is Wj, phi j bar? So it's your weighted, basically this looks like your regression model, right? Okay? So it's the average with W's of your basis functions, but what basis functions? The average of the basis functions over the data points. So if you look at you remember your design metrics, each basis function corresponds to each column, right? And each row corresponds to each data point. So effectively, what this calculation means is go to each column, take the average over all data points, all right? And then use these averages, these p bars, and see how the regression model with these averages, how far away it is from the mean response. That's the bias there. Okay? Now, this looks nice, right? So you can, it has an appealing, common sense sort of answer, but to compute this bias term, you need to know W's, and we don't know the rest of the W's yet, right? And we're not, generally, we can do MLE on the remaining of the W's, but, when you do MLE on those W's, you overfit anyways, right? But at least now, we say we trust this estimate, and if somehow we get some good estimate for W's, maybe the bias term can be computed from this calculation. No way, basically, no reason to do regularization or prior on W0. This formula, this value is good enough, but we need to know what W's are. All right. Let me actually, because it's 1:36, what I'm going to do is, let me go to the easy problem, and I'm going to give you exactly what we are going to do for a trivial regression model, where it looks like that. So no basis functions here. It's W0 plus W transpose X. I'm not removing any complexity. The rest is algebra. Okay? So I'm going to assume that my regression function is W0 plus W transpose X. So X is some d-dimensional vector. So my bias term is outside. And we already have seen this result. You agree that the previous result, now there are no basis functions. It's really X directly. You agree the previous MLE result for W0 looks like that, right? So it would be the mean response minus the regression function computed for the average X's. So effectively what you need to do, and I think it's on the next slide, when I mean the average X's, right, you go to dimension 1 over all the tiny points and you find the average x1 coordinate, that to dimension 2 you find the average x2 coordinate, all right? That's how you define x bar. So this is what this formula is. That's the MLE formula for W0 for the simple regression model. So let's do the following thing now. I am going to go to my error function, all right? You remember the error function is summation over the data points of Ti minus what the regression model tells me. And the regression model had minus W0 minus W transpose Xi. You remember the bias term was alone. So what I have done here is, instead of W0, what have I done? I use actually the MLE estimate explicit that we computed. Right, that's the MLE estimate. So I plug in, have Ti minus T bar, and then I have W transpose X bar minus Xi. So if you take now the MLE estimate with respect to W, and you take the derivatives with respect to W equal to 0, you get this. So basically, to get the MLE of W without bothering about the bias term, what type of operations you have to see? I mean, all the algebra is written here, but I want you to look at this formula. What will you do? First, what do you do to your design metrics? In every column, what do you have to do in your design metrics? Subtract the average over the data points. And then what do you have to do the response? Subtract the average mean response, okay? So basically what you need to do is, instead of working with the design metrics, in this case, x1 to xm, let's say, you basically have to subtract the mean of x1, the mean of x2, the mean of xm. You define a new design metrics, and instead of having the response t, you subtract basically the average t response, and then you know what? The problem looks exactly like least squares problem, where you compute all the parameters but the bias. The only difference is that, I mean, previously in the notation we called this phi matrix, all right? It's the same notation, phi or capital X. So this matrix there does not have the bias term on it, okay? So basically, the ones that usually come on the design metrics, we don't account for them, all right? And we have this centered design metrics, okay? And so that's very nice, okay? So now that will give you the MLE. Can you help me now in the remaining few minutes? If I want to do regularization and only I want to regularize everything but not the W0, what will you do? Look at this thing here. Can you guess that somehow how will things look like? I mean, here for an MLE estimate, there's no W0. When I center the matrix phi or x, you know, and the responses, you can see the least squares problem looks like this with the center matrices and center responses. So if I want to do a regularized least squares, if I want to do ridge regression, what do you think is, can I do ridge regression somehow only on this W's and nothing else? And how do I pose the problem mathematically? I mean, I need to write something nice, right? That says minimize this with this regularization term, but I cannot have on the same equation a W0 and a W. So how can I do this? So here it is sort of a principal way to demonstrate that the obvious result can be interpreted as the correct result. So here, what you see on the top equation is the likelihood model, all right? And the likelihood model, it says T minus my regression model, but here I have removed outside the bias term that I call it mu, the average, okay? And this function's phi here and this W's include all the terms except the bias term. So this looks exactly like what I had before, right? But it does not have, like the phi metrics, the first column is not ones. It's directly the basis function phi1 for all data points. The average I wrote it explicitly outside there with this term minus mu, okay, times this vector 1 of size n. Now, what we need to do is we need to center this matrix phi. So in the slides, when you read them, I am assuming, to make things simple, that when you take the sum of its all the elements in every column, all right, you get equal to 0. So effectively, I have removed the mean from every column. So what you need to do, right, your matrix phi is like this. It doesn't satisfy that, so what you need to do, go in every column, remove its average, and define a new matrix phi that satisfies these properties. So I'm assuming here, when I write this T minus mu minus phi times W, I'm assuming that I have done that. Very easy to do, okay? It's pre-processing. And here is the trick now. So what I'm going to do is I'm going to go back to the regression model, okay, and one step at a time. So the first thing I'm going to do is, this again looks like the likelihood, okay. I subtracted and added t bar times the unit vector 1, and again subtracted and added the vector t bar. And then what have I done? Look at the integral there. I am going to take this bias term, that mean value, as a random variable with some uniform prior, and I'm going to integrate it out. Okay, just to do proper analysis. So what I'm going to do is I am going to find, all right, a likelihood that is has marginalized W0. W0 is out, all right, or this mu is out. Okay, and it comes out if you expand this exponential and you call that nice term as alpha. You remember this vector alpha, there's no mu here, there's no dependence on the bias term. It comes out by a miracle of nature that you get two terms in mu. One that is gives you a square exponential that basically when you marginalize it out from the Gaussian analysis disappears, you get a constant. And then another term that comes to be 0. And then effectively what you get is you get a marginal likelihood that looks like this. And if you do a new definition, as I told you, to centerize to center the responses still by subtracting the average response, then, and you call this the new t, then your likelihood looks identically to what we have done up to now with Bayesian analysis. So basically, everything we discuss about the Bayesian model, you can actually treat it for in this framework where there is no W0. All right? You post-process your phi metrics, all right? You centralize the responses. This is your new likelihood. And now you can put a prior on W, but the prior on W will involve all terms, but the bias term. And what happens when you finish? When you finish, you can go back and say, you know what? You can use the MLE or the MAP estimate of W's, and this is the bias terms. Add them to your regression function W. Okay? So the light is still on, so I'm going to finish there. And I'm going to see you tomorrow to do some other more interesting regression aspects and maybe the evidence approximation as well.
For the topics you haven't
Yes, for the topics.